Hi and welcome to the Corbettmaths Ultimate CCEA M7 revision video. In this video we're going to go through the M7 topics from the CCEA GCSE Maths course, and the aim of this video is to spend about 5 or so minutes in each of those topics to make sure you're familiar with each of them. In terms of the M7 topics, in the description below there's a revision checklist for M7, and in blue you've got the algebra topics, in green the geometry or shape, space and measure topics, in orange the statistics and probability topics, and in red the number topics. This revision checklist will be really useful for you, so I'd recommend you print it, add it to your notes and keep it, and have it somewhere that you can just double check whenever you're revising that you've gone through all the topics. If you need any extra help on any of the particular topics, beside each topic there's the video number for the video on Corbettmaths, which will be really useful to give you more information on it. So as I said, I'm going to spend about 5 minutes on each of these topics, but if for instance you needed more help on simultaneous equations, if you go to video 295 on corbettmaths.com/contents, or you go to Corbettmaths and click the videos and worksheets link and go down to video 295, you'll see a more in-depth video on simultaneous equations. It probably goes through it in about 10 minutes or so. Also remember, for M7 it would be very useful if you watch the M6 and M5 videos, and also that you're familiar with the M3, M2 and M1 content as well. In terms of this video, as you're watching it, you might want to make notes on each of the topics as we go through them. But also with maths, one of the great things to do whenever you're revising is to do some practice questions, and I've created the Ultimate CCEA M7 Revision Question Booklet. Catchy title, I know. On the front of that booklet, you've got the answers there, so if you do scan that QR code, it'll bring you to the answers for each of the questions. But that booklet has a question on every single topic that I'm about to go through. So not only do you have the video that will make sure that you're familiar with each of the topics, you've got a chance to practice that as well. Also, as we go through this video, you'll notice that I use some of the Corbettmaths revision cards as we go through it. The Corbettmaths revision cards will be really useful for your revision, so the higher revision cards will be the ideal ones for M7. In the description below, you'll see a link to those. Also, in terms of revision, I prefer a little and often approach, so rather than cramming just the night before the exam, if you can spend 5 or 10 minutes every day on your M7 revision, it'll really pay off for you. So whenever you're revising for M7, I'd highly recommend the Foundation Plus 5-a-days and also the Higher 5-a-days, and they're the yellow and green books on the website. Okay, so let's get started. So our first topic we're going to look at is laws of indices, and that's video 174 in Corbettmaths. So with laws of indices in M7, the key difference is it'll include negative numbers as some of the powers. So here we've got our laws of indices, that if we're multiplying two terms with the same base, such as m cubed times m to the power of 4, you'd add the powers. So whenever we're multiplying, we add the powers. So if we had m cubed times m to the power of 4, the answer would be m to the power of 7, because 3 plus 4 equals 7. If we had m to the power of 8 divided by m squared, but we take away the powers, 8 take away 2 is 6, so the answer would be m to the power of 6. And if we had a power of a power, so that's when we've got something with a power and then a bracket and a power outside of the bracket, we multiply the two powers together. So if we had m cubed squared, we multiply the powers together. And this is part of the Corbettmaths revision card on laws of indices. Now let's have a look at some examples. So in M7, remember, we could have negative powers. So we've got y to the power of negative 5 multiplied by y to the power of 3. So because we're multiplying, we're going to add the powers. Negative 5 plus 3 is equal to negative 2. So that's to be y to the power of negative 2. Next, we've got y to the power of 8 divided by y to the power of negative 4. Again, when we're dividing, we take away the powers. So 8 minus 4. Well, it's going to be 8 plus 4, which is 12. So the answer would be y to the power of 12. And finally, if we had y to the power of negative 3 squared, because we've got a power of a power, we multiply the powers together. Negative 3 times 2 is negative 6. So the answer would be y to the power of negative 6. Now later on in this video, whenever we get to the number topics, I'll talk more about negative powers, such as this y to the power of negative 6. But if you do have something such as y to the power of negative 6, that's the same as 1 over and then y with a positive power. So if you've got a negative power, you can put 1 over and then y, and this put a positive power. So y to the power of negative 6 is the same as 1 over y to the power of 6, like so. Another thing for M7 that you need to know is that anything apart from 0 to the power of 0 is 1. So here, if we had 5 cubed, well, 5 times 5 times 5 is 125. 5 squared, well, that's 5 times 5, which is 25. 5 to the power of 1, that's just 5. So whenever we have 5 cubed and 5 squared and 5 to the power of 1, the answers are 125, 25 and 5. And you'll see that we're decreasing the power by 1 each time. And with our answer, we're dividing by 5 each time. So if we divide by 5, we get 25. If we divide by 5 again, we get 5. And if we divide by 5 one more time, we will get 1. So as you can see, I've just shown that 5 to the power of 0 is equal to 1. Okay, let's have a look at our next topic. So our next topic is simultaneous equations. And here we've got a pair of simultaneous equations. We've got 3x minus y equals 23 and 2x plus 3y is equal to 8. So whenever we get simultaneous equations, what we want to do is cancel out one of the letters. We want to add or subtract the equations so that one of the letters disappears. So as you can see here, we've got minus y and we've got 3y. Now if we had minus 3y and 3y, we could add them together to get 0. So what I'm going to do is I'm going to multiply this top equation by 3 to begin with. So let's number them, 1 and 2. So we've got equation 1 and equation 2. We're going to do 3 times equation 1. So whenever we do 3 times equation 1, well, multiplying this by 3 gives us 3 times 3x is 9x. Then 3 times minus y, well, that's going to be minus 3y. And 3 times 23, well, 3 times 23 is 69. Then we've got equation 2, which is 2x plus 3y equals 8. We've got one equation with minus 3y and we've got one equation with 3y. So that's fantastic. What we can do now is we can add these two equations together, and our minus 3y and our 3y will add together to give us 0. So we'll just be left with x's, and that's fantastic. Okay, so let's add the two equations together. So let's write the word add. I tend to avoid putting a plus or minus symbol just in case if it was a subtract and I put a minus here in front of the 2 and make it confused and think it's a minus 2x. So I write add or sub. Now what I'm going to do is I'm going to add these two equations together. So 9x plus 2x, well that would be 11x. Minus 3y plus 3y, well that's 0, so they cancel out. And finally we've got 69 plus 8, that's equal to 77. So we've got 11x equals 77. Now we can divide by 11 and divide by 11 and we get that x equals 7. So x equals 7. So that's fantastic. So we know x is equal to 7, so let's now find y. So let's substitute this x equals 7 into one of our equations. And I'm going to substitute it into equation 2 just because we have positive 3y. And let's write that down. So sub x equals 7 into 2, just to show what we're doing. So whenever we substitute x equals 7 into this equation, we get 2 times 7, so that's 14, plus 3y equals 8. Now we're going to solve this equation, so minus 14 and minus 14. Well, we had 14 plus 3y, and we took away the 14, so we're just left with 3y. And on the right-hand side, we've got 8 take away 14, that's going to be equal to negative 6. Now we're going to divide both sides by 3, and whenever we divide both sides by 3, well, 3y divided by 3 is just y, and negative 6 divided by 3 is equal to negative 2. So that means we've got our answers. We've got x equals 7, and y equals negative 2. And let's just check our answer. Now we substitute x into equation 2 to find our value of y. Let's now substitute both of them into equation 1. So let's check in 1. So check in 1. Well, if we put these numbers, if we substitute these numbers into equation 1, we've got 3 times x, so that's 21. 3 times 7 is 21. Minus y. Y is minus 2, so we're going to do minus minus 2. And that's meant to be equal to 23. So let's check it. 21 minus minus 2, that's 21 plus 2, and that's 23, so that's right. So we know we've got this question right, and that's it. Okay, let's have a look at our next question. So our next question says, solve the simultaneous equations 2x plus 3y equals 1 and 7x plus 2y equals negative 22. And I've chosen these numbers on purpose because what we're going to have to do now is multiply both equations by certain numbers to get the same number in front of either the x's or y's. So let's call our equations equation 1 and equation 2. Now we could cancel out our x's, so we could multiply the top equation by 7 to get 14x, and we could double equation 2 to get 14x, and we could cancel those, or we could cancel our y's, so we can multiply, let's say if we've got 3 and 2, let's get 6, so we can multiply our top equation by 2 and our bottom equation by 3, and that would give us 6y and 6y. And because they're both 6y's, we would then take the equations away from each other to get 0. Let's actually do that. Let's cancel our y's. So let's multiply equation 1 by 2 because we want to get 6y. So we're going to do 2 times 1. And when we do 2 times equation 1, we get, well, multiplying this whole equation by 2 would be 4x plus 6y equals 2. Now we've got equation 2, but we want to get 6y, so let's now multiply this whole equation by 3. So let's do 3 times equation 2. And when we do that, we get, multiplying these all by 3, we get 3 times 7x is 21x, 3 times 2y, that's going to be plus 6y, and 3 times minus 22, that's going to be minus 66. So this is great because we've now got two equations, both with 6y's in them. Now what we can do is we can now take away these equations from each other. Now the only thing is that whenever we take these away, we're going to have 4x take away 21x, which would be negative 17x and so on. So what I'm actually going to do is I'm going to write this top equation again just beneath this other one. So I'm going to write 4x plus 6y equals 2. Just so that whenever I take these equations away from each other, I'm going to get 17x rather than minus 17x. So now let's put a line beneath them and let's say subtract. So we're going to subtract these equations from each other. So 21x take away 4x, that's 17x. 6y take away 6y, well that's 0, they cancel out. And then we've got minus 66 take away 2. So when we've got minus 66 take away 2, we're going to go down another 2, so it's going to be minus 68. So we've now got 17x equals minus 68. So let's divide both sides of this equation by 17. So divide by 17 and divide by 17, and we're going to get that x equals negative 4. So we now know that x is equal to negative 4. We can substitute that into either equation 1 or equation 2 to get our y. Let's substitute it into equation 1. So equation 1, so sub x equals negative 4 into 1. And when we do that, we get, well, 2 times x, well, that's going to be 2 times negative 4, and 2 times negative 4 is negative 8, plus 3y equals 1. Now, if we want to solve this, we want to get rid of our negative 8, so let's add 8 to both sides, so add 8 and add 8. So that would give us 3y equals, and 1 plus 8 is 9, and divide by 3, and divide by 3, and we get y is equal to 3. So our answers are x equals negative 4, and y equals 3. And again, we can check our answer in equation 2, check in 2. And when we do that, we get, well, 7 times x, well, 7 times minus 4 will be minus 28. Then we've got plus 2y, well, y is equal to 3, so 2 times 3 is 6, so we're going to add 6, and that should be equal to negative 22. And let's just check it. Negative 28 plus 6 would be negative 22. So that is equal to negative 22. So we're right. We know that our answers would have to be x is equal to negative 4 and y is equal to 3. Okay, let's have a look at our next question. Now, quite often in M7, whenever we're doing simultaneous equations, the questions are often given in a wordy context, maybe where you're buying so many of something and so many of something else, and you're given the price and so on, and you've got to create your own simultaneous equations and solve them. So let's have a look at a typical question. So we've got 5 adult tickets and 3 child tickets cost £58, and 2 adult tickets and 8 child tickets cost £47. Find the cost of each type of ticket. So we've got our two equations. We've got 5 adult tickets. Well, let's let an adult ticket be x pounds, and let's let a child ticket be y pounds. So let's make our equations. We've got 5x plus 3y is equal to £58, so equals to 58. And then we've got 2x plus 8y, and that's equal to £47. So we've got our two equations. Now what we want to do is either get the same numbers in front of our x's and y's, or the same but one being positive and one being negative, because if they're both the same, we can take them away from each other, or if they're both the same but one's positive and one's negative, we can add the two equations to get 0. We could cancel out our x's, or we can cancel out our y's. Just for fun, I'm going to cancel out our x's this time. So I'm going to actually cancel out our x's. So I'm going to multiply our top equation, this equation 1, by 2 to get 10x. I'm going to multiply the second equation, equation 2, by 5 to get 10x as well. And then what I'm going to do is take the two equations away from each other. So let's do 2 times equation 1. And when we do 2 times equation 1, we get, well, multiplying these all by 2 would get 10x plus multiplying 3y by 2 would be 6y equals, and multiplying 58 by 2 would be 116. And then multiplying equation 2 by 5, because we want to get 10x, so 5 times equation 2 would be, multiplying these all by 5 would give us 5 times 2x is 10x. 5 times 8y, well, that's going to be 40y, and then multiplying 47 by 5 would be 235. Now we want to cancel out our 10x's, so if we've got 10x and 10x, we want to take them away to get 0. Now because we're taking away, rather than 6y take away 40y, I'm actually going to write this top equation just beneath the other one again. So let's scroll down, and let's write 10x plus 6y equals 116. And let's write sub, because we're going to subtract them from each other. So 10x take away 10x is 0. 40y take away 6y, well, that's 34y. And then we've got 235 take away 116. And when we do that, we get an answer of £119, or 119. So we now know that 34y equals 119. We can divide both sides by 34 to get y equals, and 119 divided by 34 is equal to 3.5, or £3.50. So we now know what y is, and that's the cost of a child ticket, which is 3.5 or £3.50. Let's find the cost of an adult ticket. So let's sub y equals 3.5, and we can choose either equation 1 or equation 2. I'm going to choose equation 2, so into 2. And when we substitute 3.5 in for the value of y into equation 2, we're going to get, we've got 2x plus, and then we've got 8 times 3.5. That's equal to 28, and that's equal to 47. So we've got 2x plus 28 is equal to 47. So let's take away 28 from both sides. So that gives us 2x equals, and 47 take away 28 was equal to 19. And then if we divide that by 2, we get x equals, and dividing 19 by 2 is 9.5. So as the question says, find the cost of each type of ticket. So we've got an adult ticket, which is x, and that's going to be equal to £9.5 or £9.50. So let's write it as a price, £9.50. And a child ticket, which was equal to y, is equal to £3.50. And that's it. So quite often, whenever you're dealing with simultaneous equations in M7, you're given a wordy context where you've got to make your equations and then solve them to get the values. Okay, let's have a look at our next topic. So next topic is changing the subject. Now we had changing the subject in M6, and in M6 we had changing the subject, and they were quite nice questions. And in M7 we could be asked to change the subject for a formula or equations that have two of the same letter. So in this one we've got w equals y plus 2 over y, and we've asked to make y the subject, so we could be given slightly harder formulae or equations to rearrange. Or alternatively, you could be asked to change the subject with equations or formulae that involve powers. So for instance, it could have a cubed in it, and you might need to cube root both sides. Okay, so let's have a look at this example. So we've got make y the subject of w equals y plus 2 over y. So what I'm going to do is, I don't want to have this y on the denominator, so I'm going to multiply both sides of this by y. So multiply by y and multiply by y. W times y will be wy, just putting them beside each other. And on our right hand side, we had y plus 2 divided by y. We multiply by y to get rid of the divide by y, so we're just going to be left with y plus 2. We've now got yw equals y plus 2. Now we want to make y the subject, which means we want to have at the end y equals something. But here we've got two terms with y's in it. We've got wy and we've got the y. So what we want to do is we want to bring them over together on the same side. So what I'm actually going to do is take away y from both sides of this formula, and what that will do is bring the y's to the left hand side here. So we've got wy, and we're going to take away y, so we're going to write wy minus y. So we've brought all the y's over to the left hand side, and we've got the plus 2 or just 2 on the right hand side. So we've got the terms with y's on one side and everything else on the other side. Now we want to make y the subject. Now we've got wy minus y. We can actually factorize this because they both have y's in them. So we can write y and then brackets, and we can factorize this by dividing both of these by y. So wy divided by y would just leave us with w. And then we've got minus, and y divided by y is 1. So if we were to factorize wy minus y, taking the y out, we'd leave us with y bracket w minus 1. And that equals 2. Now we're almost there. We've got y times w minus 1 equals 2. But we don't want the w minus 1 there, we just want the y. So if we want to get rid of this w minus 1, what we're going to do is we're going to divide both sides by w minus 1. So dividing the left hand side by w minus 1, well, that would just leave us with y, which is great. And on the right hand side we had 2, and we're going to divide it by w minus 1, so we'll just write that down. We'll write 2. Now remember, we don't write the divide by sign in algebra, we write the big line, so over, and then we write w minus 1 on the denominator. So we've got 2 divided by w minus 1. So that's our answer. We've got y equals 2 over w minus 1. And let's just write that out, 2 over w minus 1. So we've made y the subject. And these are videos 7 and 8 in Corbettmaths, changing the subject and changing the subject advanced. And this particular type of question would be video 8, the advanced video. So I'd highly recommend watching that video in Corbettmaths. And there's practice questions there. I've actually updated those recently, and there's actually video solutions to those. So whenever you go through those questions, you want to see how I've done each question. I've actually made a video talking about every single question in that booklet. Okay, let's have a look at our next question. So our next question says, make y the subject of w plus y cubed equals c. So as you can see with this formula, we've got a cubed, and in M7 you could have powers involved, so or even roots and so on. So here we've got w plus y cubed equals c. So we want to get the y on its own. So what I'm going to do first of all is get rid of this w. So I'm going to minus w from both sides of this formula. So we're taking away w to get rid of the w, so we'd just be left with y cubed on the left hand side, and then on the right hand side we'd have c minus w, so c minus w. Now we want to get the y on its own, and it's y cubed, so we're going to work out the cube root of both sides. So the cube root of y cubed, well, that would just be y. And on the right hand side, we want to find the cube root of this. So to find the cube root of this, we'll do a cube root, and then underneath we'll just write c minus w. We're working out the cube root of c minus w, and that's it. So we have made y the subject of this formula, this w plus y cubed equals c. When we make y the subject, y is equal to the cube root of c minus w. Okay, let's change the subject. Okay, so our next topic is the nth term, and this time we're going to be looking at nonlinear nth term. So that could be finding the nth term of a sequence of fractions such as this, or it could be perhaps maybe if you've got the square numbers but you've got one bigger than them, finding the nth term being n squared plus 1 and things like that. And this would be video 289 in Corbettmaths. So here we've got a sequence of fractions. We've got 3/4, 5/8, 7/12, 9/16, and so on. Now if you look at the numerators, we've got 3, 5, 7, and 9. There's a pattern there. We're getting bigger by 2 each time. They're getting bigger by 2. We're adding 2, adding 2, adding 2, and so on. And actually, if we look at the denominators, we've got another pattern. We've got 4, 8, 12, 16. And we're actually adding 4 each time. So adding 4, adding 4, adding 4. So actually, if we look at our top line, our numerators and our denominators, we have got a pair of linear sequences. Our top sequence is 3, 5, 7, 9, and our bottom line, our denominators are 4, 8, 12, 16. They're both linear sequences. They're both getting bigger by the same amount each time. So what we're going to do is we're going to work out the nth term for the numerators, we're going to work out the nth term for the denominators, and then just write that as a fraction, and that will be our answer. So let's focus on our numerators, our top line. We had 3, 5, 7, and 9. So if we want to find the nth term of this, well, we're getting bigger by 2 each time, so let's write the 2 times tables beneath it, 2, 4, 6, 8, and 2n. Now our sequence isn't 2, 4, 6, 8, so it's not 2n, it's actually 1 bigger than it. We've added 1, added 1, added 1, and added 1. So the nth term for the numerators would be 2n add 1. In terms of our denominators, our sequence is 4, 8, 12, 16. So because we're getting bigger by 4 each time, let's write down the multiples of 4. So 4, 8, 12, and 16. That's great actually, because it will just be 4n, because we don't need to add or subtract anything. So the nth term for our numerators is 2n plus 1. And our nth term for our denominators is 4n. So that means the nth term of this sequence would be 2n plus 1 over 4n. And let's just check it. Let's look at this fourth term in the sequence. It's 9/16. If we wanted the fourth term, we would substitute n equals 4 into this. So we would do 2 times 4, which is 8, plus 1, 9. And then 4 times 4 for the denominator, which is 16. So that would be it. And that's fantastic. So we have worked out the nth term of this sequence of fractions. If we were asked to find the 100th term, we would do 2 times 100, 200 plus 1, which would be 201. And the denominator would be 4 times 100, which would be 400. So the 100th term in this sequence would be 201 over 400. And that's it. Okay, let's have a look at another type of sequence now. So here we've got some more nonlinear sequences, and they're all to do with square numbers. So the numbers 1, 4, 9, 16, and so on. And if we have a look here, our first sequence is 1, 4, 9, 16. So because these are square numbers, that means the nth term is just n squared. Let's just check it. The third term, 3 squared is 9, and so on. Let's have a look at our next one. So this time we've got 3, 6, 11, 18. So if we write down the square numbers beneath it, 1, 4, 9, 16, and that's n squared. As you can see here, the sequence we've got here is 2 bigger than those. We've added 2, added 2, added 2, added 2. So that means the nth term of this sequence, 3, 6, 11, 18, would be n squared add 2. It's a square numbers, but 2 bigger than them. And finally, we've got 2, 8, 18, and 32. Let's write our square numbers beneath those. We've got 1, 4, 9, and 16, and that's n squared. And if you have a look at our sequence, we've got, instead of having 1, we've got 2. Instead of having 4, we've got 8. Instead of having 9, we've got 18. Instead of having 16, we've got 32. So they're actually double the square numbers. So that would be 2n squared. And that's it. So in M7, we could be dealing with nth terms that are for nonlinear sequences, such as fractions, or sequences that are linked to the square numbers or cube numbers and things like that. Okay, let's have a look at our next topic. And our next topic is graphical inequalities. And I really like this topic in this video, 182 in Corbettmaths. So here we've got a set of axes. We've got our x-axis and our y-axis. And we've been asked to show the region that satisfies x is smaller than or equal to 7, y is bigger than or equal to 3, and y is less than or equal to half x plus 2. So what we're actually going to do is we're going to draw these lines to begin with. We're going to draw the line of x equals 7. We're going to draw the line of y equals 3. And we're going to draw the line of y equals half x plus 2. And so we'll draw those lines to begin with, okay? And then once we draw those, we'll then be able to see which region satisfies these inequalities. So let's start off with x equals 7. Let's look at the line of x equals 7. So x equals 7 is a vertical line passing through 7 on the x-axis. So here we've got our x-axis and here we've got 7. And the line x equals 7 is a vertical line that passes through 7 on the x-axis. You might have seen it before whenever you've done reflections, when you're reflecting shapes on axes. So that's the line x equals 7. Because all of the points on that line have an x-coordinate of 7. There's 7 across, 1 up, 7 across, 2 up, and so on. Okay, our next line, y equals 3. So we want to draw the line y equals 3, and that's going to be a horizontal line passing through 3 on the y-axis. So here we've got the y-axis, here we've got the number 3, and that line y equals 3 will be a horizontal line that passes through that point. So let's get our ruler and pencil, and let's draw that line. And again, you will have drawn lines like that whenever you've done reflections in M6. So we've drawn the line y equals 3. And finally, we need to draw the line of y equals a half x plus 2. So what we've done is I've just taken the inequalities we've been given, changed all the inequality signs to equals, and we're just going to draw those lines to begin with. So what we're going to do is we're going to draw this line of y equals a half x plus 2. So I'm going to do an xy table, x and y, and choose some values for x. So 0, 1, 2, 3. And we're going to find the y value. It's half of the x value plus 2. So half of 0 is 0 plus 2 is 2. Half of 1 is 0.5 plus 2 is 2.5. Half of 2 is 1 plus 2 is 3. And half of 3 is 1.5 plus 2 is 3.5. So here we've got our coordinates 0, 2, 1, 2.5, 2, 3, and 3, 3.5. So 0, 2, 1, 1.5, 2, 3, 3, 3.5, and so on. So let's get our ruler and pencil and draw a nice straight line through those. And it would look something like that. Okay? So in this question, we've been asked to show the region that satisfies these inequalities. Now we've drawn the line of x equals 7, but we've been told in the question that x is less than or equal to 7. So that means our region will have to be less than 7. So it means that our region will be on the left of this line. So it can't be anything on the right hand side of this line because anything over here would have an x value bigger than 7. So what I'm actually going to do is just shade this right hand side to show that it can't be anything on this side of the line because x has to be less than or equal to 7. Okay, let's have a look at our next one. So we've got y is bigger than or equal to 3. So we drew the line of y equals 3. And if we wanted a y is bigger than or equal to 3, it would be anything above that line. Anything below it would have a y value of something less than 3. So that means that anything below this horizontal line couldn't work. So we have to reject anything below that line. So let's just shade in just beneath it like this, just to show that we're rejecting anything below that line. Anything below this line would have a y coordinate of less than 3. And we wanted to find the region where the height is bigger than or equal to 3. Okay, let's have a look at our last inequality. Our last inequality is y is less than or equal to half x plus 2. So here we've got this diagonal line. We've drawn the line of y equals a half x plus 2. And one of these sides, either the top or the bottom, we want to keep, and one side we want to reject. Now in terms of figuring out which side I want to keep or which side I want to reject, what I do is I look at the inequality, y is less than or equal to half x plus 2. And what I do is I pick any point that's not on this line. I'm actually going to pick the origin, this point here, the coordinate 0, 0. Okay, so I'm going to choose this coordinate 0, 0. And I'm going to substitute in x equals 0 and y equals 0 into this inequality, and I'm going to see if it works or not. So let's substitute x equals 0 and y equals 0 into this inequality. So we had y, so instead of y we're going to write 0, and that's less than or equal to half of x. Well, a half of 0 is 0 plus 2. So we've got 0 is less than or equal to 0 plus 2. Now 0 plus 2 is 2, so we've got 0 is less than or equal to 2. Now let's have a look at this inequality. We've got 0 is less than or equal to 2. Well, 0 is less than 2. So that means that this inequality works, okay? 0 is less than or equal to 2. If we had something like 9 over here and we had 9 is less than or equal to 2, it wouldn't work because 9 is not less than or equal to 2. But here we had 0 is less than or equal to 2, so that works. So that means that this point, the origin, 0, 0, satisfies this inequality. It works. That means that below this diagonal line is the region we want to keep, and above the diagonal line is the region we don't want to keep. So what we're going to do is we're just going to shade in above the diagonal line like so to show that this section of the line, this section of the graph, anything above this line is rejected and anything below is accepted. And then as you can see, we're left with this triangle, and inside this triangle in this region it satisfies all three of these inequalities. So then in the question it might ask you to label it with an R to show that's the region that works, that satisfies all three inequalities, or sometimes the question could say shade in the region that satisfies each of them, and then you would shade in that region really carefully to show that it satisfies them. But typically the question, the ones that I normally see say label it with an R to show that that's the region that satisfies all three inequalities. And that's it. Okay, let's have a look at our next topic. So our next topic is reciprocal graphs, and this video 346 on Corbettmaths. So a reciprocal graph is something in the form of y equals a number and then over x. So something like y equals 2 over x. And you will have heard of the term reciprocal before whenever you're dividing by fractions, because whenever you're dividing by fractions, instead of dividing by a fraction, you multiply by the reciprocal. That's what you get when you flip it over. And that's what we mean whenever we've got a graph in this format, y equals 2 over x. We'll also maybe talk about the word reciprocal later on when we talk about negative indices in the number topics. So we're going to draw a graph, and we've got an xy table, and we've got quite a lot of points because there's curves involved. It's not nice straight lines. So we're going to substitute in these values of x into our equation to get our values for y. So let's start off with the positive values. So let's use x equals 5. So 2 divided by 5 is 0.4. Then we've got 2. Well, 2 divided by 2 is 1. Then we've got 1. 2 divided by 1 is 2. Then we've got 0.5. So we've got 2 divided by 0.5. Well, there's 4 halves in 2, so the answer would be 4. Now let's move on to our negative numbers. So we've got 2 divided by negative 5. Well, a positive divided by a negative is a negative, so it's going to be a negative answer. And 2 divided by 5 is 0.4, so it's going to be negative 0.4. We've then got 2 divided by negative 2. Well, that's going to be, well, positive divided by a negative would be a negative, so negative 1. Now we've got 2 divided by negative 1, that would be negative 2. And finally, 2 divided by negative 0.5 would be negative 4. Okay, so we've now got our points. Now let's plot them. So we've got 5 across and 0.4 up. So 5 across would be here. 0.4 up, well, we've got 10 little squares for 2. 2 divided by 10 is 0.2. So it'll be 2 of them upwards, or 2 of them up. So it'll be like that, somewhere like that. Then we've got 2, 1. So 2 across 1 up would be there. Then we've got 1 across 2 up. So 1 across 2 up. And then we've got 0.5 across 4 up, so 0.5 across would be halfway in between, and 4 up would be there. So we've now got our points. Now what we're going to do is draw a nice curve through them. Now this is quite tricky on the computer, so just bear with me. Okay, this won't be perfect, but it's just going to be a nice curve that looks something like so. That's not too bad. And as you can see, the curve, it never actually reaches the y-axis, because if you've done 2 divided by 0, well, that's undefined. You can't divide 2 by 0. So this curve will never actually reach the y-axis. And as you divide by smaller and smaller and smaller decimals, so 2 divided by 0.1 would actually be 20. So that's really hard. 2 divided by 0.001 would be equal to 200. So what happens is the graph would just shoot off to infinity, and it would never actually reach the y-axis. And similarly, whenever we're going to cross horizontally to the right here, because we're doing 2 divided by something, even if we divide it by 1,000,000, there'll still be a tiny number there. It'll be 0.0000 and so on. So the graph will approach the x-axis but never actually reach it. They're what we call asymptotes. It's quite a fancy word, and you don't actually need to know that for M7, but that's just what they're called. Okay, and these points on our left-hand side of the table, we've got negative 0.5 and negative 4, so that would be there. Then we've got negative 1, negative 2, so negative 1, negative 2 would be there. Negative 2, negative 1 would be there. Negative 5, negative 0.4 would be there. So we've got our points, and we're going to draw a nice curve through them. So that would be the graph of y equals 2 over x. If you had something like y equals 4 over x, it would have the same shape, but it would just be slightly further out. So it'd be slightly higher up and slightly further down, and so on. Okay, let's have a look at our next topic. So the next topic is cubic graphs. So here we've got the graph y equals x cubed. So cubic is whenever we've got this cubed. And here we've got y equals x cubed. So here we've got our xy table. So let's cube all these values to get our y values. 2 times 2 times 2 is 8. 1 times 1 times 1 is 1. 0 times 0 times 0 is 0. Negative 1 times negative 1 times negative 1. Well, negative 1 times negative 1 is 1. And times that by negative 1 is negative 1. Because a negative times a negative times a negative is a negative. Then we've got negative 2. So negative 2 times negative 2 is 4. Times negative 2 is negative 8. And finally, negative 3 times negative 3 times negative 3 would be negative 27. And now let's put these points on our grid. So let's draw our curve. So it'll come upwards. So go through the points. And then what will happen is it'll flatten out and come through 0, and then curve back upwards and look something like that. And excuse my sketch, it is freehand on the computer, it's quite tricky. And now let's have a look at our y equals negative x cubed. So what this means is we're going to cube our value of x, and then we're going to make it negative. So we're going to do 2 cubed. So 2 times 2 times 2 is 8, but we're going to make it negative, so it's going to be negative 8. Then we've got 1 times 1 times 1, which is 1, but we're going to make it negative, so negative 1. Then we've got 0 times 0 times 0, 0. Well, that's just 0. Then we've got negative 1 times negative 1 times negative 1. That's negative 1. But we're going to make it negative. What that means then, because it's already negative, it means we're going to make it positive. So it's going to be 1. And then we've got negative 2. So negative 2 times negative 2 times negative 2 is negative 8. But then we're going to make it negative, but it's negative already, so it means make it positive. We're going to change the sign. So that's 8. And then finally, we've got negative 3 times negative 3 times negative 3, which is negative 27. We're going to make it negative, it's already negative, so it's going to be 27. And another way to consider this negative sign, do you remember if you've got something like x cubed, that means 1x cubed, or 1 lot of x cubed. If you've got negative x cubed, that's the same as negative 1x cubed. So really what we're doing is we're finding our value for x cubed, and then we're multiplying it by negative 1. So here we had 2 cubed, which is 8, multiplied by negative 1 is negative 8. Whenever we had our negative 1 cubed, that's equal to negative 1. When we times it by negative 1, that's 1, and so on. And what it does is it just changes the signs whenever there's a negative sign in front of it. Now let's plot our points. Okay, we've now plotted our points. Now let's try and draw curve, and that's meant to be a curve. And what you'll find is it's the same as the x cubed graph, but it's just flipped around the other way. Okay, let's have a look at a more complex cubic, and here's an example of the Corbettmaths revision card where there's y equals x cubed minus 3x minus 1. And what we've got is we've got the table of values, so we've got our x coordinates are 3, 2, 1, 0, minus 1, minus 2, minus 3, and so on. And we've worked out that number cubed minus 3 times that number, take away 1, and we've got our values for y, and whenever you plot them, it has this shape. So there's the simple cubic graphs, which will look something like this, where it's quite steep, flatten out, pass through the origin, and then curve upwards. And that's typically whenever you get something such as y equals x cubed or y equals x cubed plus 1 or something like that. But if you do have a more complex cubic where you've got x terms or x squareds and so on, it could look like this, where it actually comes up, reaches this point, this maximum, comes down again, reaches a minimum and comes up again, and so on. Okay, let's have a look at our next topic, and that's sketching quadratics. So if we had a quadratic such as y equals x squared minus 7x plus 10, it can be useful to be able to sketch this. And whenever you're sketching a quadratic, first of all, I would consider the shape of the quadratic, whether it is a U-shaped parabola or an N-shaped parabola. And what determines if it's a U-shaped parabola or an N-shaped parabola is this x squared term. If this x squared term is positive, so for instance x squared or 2x squared or so on, it'll be a U-shaped parabola. If it's negative, so if there's a minus x squared or minus 2x squared, it will be an N-shaped parabola. So that's very important whenever we're sketching a quadratic. And what's also important is where the quadratic meets the y-axis, and if and where it meets the x-axis. So let's start off by looking at this quadratic, y equals x squared minus 7x plus 10. And let's first of all consider its shape. Well, it's going to be a U-shaped parabola because it's an x squared, it's positive x squared. Okay, next, let's find where the graph meets the y-axis, or sometimes it's called the y-intercept. So to find the y-intercept, or where the graph meets the y-axis, what we do is we consider where x equals 0, because we know that the y-axis is whenever x equals 0. So if we substitute in x equals 0 into our equation, we'll find this y-intercept quite easily. So let x equal 0, and if we do that, we get y equals 0 squared minus 7 times 0 plus 10. So we've got y equals 0 squared minus 7 times 0 plus 10. And when we work it out, we get y equals 0 squared is 0, 7 times 0 is 0, so 0 take away 0 is 0, plus 10 is 10. So whenever x equals 0, y equals 10. So that would be the coordinate 0, 10. So that means our quadratic y equals x squared minus 7x plus 10 will pass through the point 0, 10. So our point 0, 10 will be, well, going 0 across and 10 up will be here. So that's the point 0, 10. Okay, so we now know where our quadratic meets the y-axis. Let's see if we can find where it meets the x-axis. So to find where it meets the x-axis, well, we know all the points on the x-axis have a height of 0. So if they've got a height of 0, that means that y equals 0. So let's let y equal 0. And whenever we let y equal 0, that will give us 0 equals x squared minus 7x plus 10. So we've got a quadratic equation, and if we can solve this, we can find where it meets the x-axis. So let's try and solve this using factorization. So 0 equals, and bracket, 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 bracket. Let's put x in the front of both brackets. And then we're looking for two numbers that multiply together to give us 10 and add together to give us negative 7. Well, it's going to be negative 2 and negative 5, because negative 2 times negative 5 is 10, and negative 2 plus negative 5 would be negative 7. So let's find our solutions. Well, if we know the two things times together to give us 0, that means that either bracket would be 0. So that means that here, x would be equal to 2, because 2 take away 2 is 0. So that means one answer will be x equals 2, or, and then looking at the other bracket, that means that x could be equal to 5. So we've got our two solutions, 2 and 5. That means our quadratic will pass through the coordinates 2, 0, and 5, 0. And there will be our 2 points where the quadratic graph crosses the x-axis. So let's put those on our graph. And before we do that, I'm just going to actually move something. I'm actually going to move this to the other side. And I'm now going to put on where that meets the x-axis. 2, 0 and 5, 0. So that'll be 2, 0 roughly there and 5, 0 roughly there. And if we do a nice quadratic through that, a nice U-shaped parabola through those points, it would look something like this. And that's it. And let's label our coordinates 2, 0 and 5, 0. And that's it. So we've done a sketch of the quadratic y equals x squared minus 7x plus 10. And we've shown the shape of the quadratic, that it's a U-shaped parabola. We've found out where it met the y-axis, so the y-intercept, which was 0, 10. And we found that this quadratic did meet the x-axis twice, and at the points 2, 0 and 5, 0. Sometimes whenever you solve the quadratic, you might find there's only one solution. And what that would mean is the quadratic touches the x-axis and goes back up. And sometimes whenever you try and solve the quadratic, you might find actually there's no solutions. And that will mean actually that the quadratic graph, the parabola, will be above the x-axis. Okay, let's have a look at our next topic. So our next topic is quadratic graphs, and we're going to be looking at videos 267 and 267D on Corbettmaths, and those videos focus on drawing quadratic graphs. So we're going to draw a quadratic graph here, this y equals x squared plus x minus 1 on this set of axes, and what we're going to do is we're going to write down the coordinates of where this quadratic meets a straight line graph. So first of all, let's draw this graph. So let's do an xy table, so x and y. And for the axes we've been given, we've got the x values of -2, -1, 0, 1, 2, and 3. So let's put those in the table, -2, -1, 0, 1, 2, and 3. So what we're going to do with all these numbers is we're going to square them, then we're going to add the number again, and then we're going to take away 1. So looking at 3, we're going to do 3 squared, which is 9. Then we're going to add 3, which is 12, take away 1, which is 11. 2 squared is 4, plus 2 is 6, take away 1 is 5. Whenever x is equal to 1, 1 squared is 1, plus 1 is 2, take away 1 is 1. 0, 0 squared is 0, plus 0 is 0, take away 1 is -1. Next, -1, well, -1 squared is 1, plus -1, well, 1 plus -1 is 0, take away 1 is -1. And actually, without actually working this one out, I can see we're going to have a value of 1 in here, because with this quadratic, we know it's going to be symmetrical, and because we've got a height of -1 and -1, the next two will be symmetrical. So if this one's 1, this one should be 1, and -3 will be 5, and so on. But let's just check it. -2 squared is 4, plus -2 is 2, take away 1 is 1. And that's it. Now let's plot our points. And now we've plotted our points, we're going to do a nice parabola through them. And please bear with me, whenever I do this on the computer, it's quite tricky to actually do it nice and accurately. Okay, so that's our parabola. It's the best I could do on the computer. And we've been asked to write down the coordinates of where this quadratic, this y equals x squared plus x minus 1, intersects with this straight line graph, y equals 3x plus 2. Now I could do an xy table for this, so I could do x, y, 0, 1, 2, 3, and multiply the numbers by 3 and add 2. I'm actually going to draw this graph using a slightly different technique. I know it meets the y-axis, it's got a y-intercept of 2, so I'm going to start at 2. And then I'm going to consider its gradient, which is 3. So I'm going to go 1 unit across, so 1 unit across, and I'm going to go up 3, so that'll be 5. I'm going to go another unit across and go up 3, that'll be 8. And again, because the gradient's 3, I'm going to go another unit across, so go moving from 2 to 3 and go up 3, so that'll bring me to 11 and so on. So I've got these 4 points, I'm going to get my ruler and pencil, draw a nice straight line through them. And that's it. So we've drawn the graph y equals 3x plus 2, and we've got our quadratic, and we've been asked to write down the coordinates of where they intersect or where they meet. So if we have a look, we can see they meet twice. They meet here at the coordinate -1, -1, so -1, -1. And they also meet again up here at 3, 11. And that's it. So they are the coordinates of the 2 points of where they meet. Okay, let's have a look at our next topic. So our next topic is reflections. So we're now moving on to the geometry or the shape, space and measure topics. And we're looking at reflections. And in M7, we need to be able to reflect shapes in the lines y equals x, so the diagonal line going upwards this way, and the line y equals -x, the line going down this way here. Okay, now just to sort of show you, the line y equals x, if we do an xy table, x and y, and we put the points 0, 1, 2, it's saying that y is equal to x, so the line y equals x has the coordinates 0, 0, 1, 1, 2, 2. So the line y equals x is a nice diagonal going up this way, and it passes through the points 1, 1, 2, 2, 3, 3, 4, 4, and so on. And if we need to reflect a shape using the line y equals -x, like in this question, and again doing an xy table, x and y, and using the values 0, 1, 2, and so on, and we know that y is equal to -x, because we have x is equal to 2, y would be -2. If x is equal to 1, y would be -1. If x is 0, y would just be 0. And if we were to consider these points, so they're the points 0, 0, the points 1, -1, 2, -2, and it's a nice diagonal line going down this way, passing through the point 0, 0, 1, -1, 2, -2, 3, -3, and so on. And it would look something like this. So it's very important in M7 to know what the lines y equals x and y equals -x look like, so that whenever you're doing reflections, you can then draw them really quickly and easily. Now to reflect the shape in that line, it's quite easy. We just count the diagonals. So let's look at each corner. So let's start off by looking at this corner, the bottom left-hand corner of B. And as you can see, if we go diagonally to our mirror line, it's one diagonal. So we need to go another diagonal the other way, so it'll move to here. This point, the bottom right-hand corner, if we count the diagonals, it's one diagonal, and then we've got half a diagonal. So if we go another 1.5, so a half and then 1 would be here. So we've reflected these 2 points. Now let's look at the points at the top of the rectangle. So let's look at the top left-hand corner. That would be one diagonal, 2 diagonals, so we need to go another 2 diagonals, that'd be 1 diagonal, 2 diagonals would be there. And finally the top right hand corner of B would be up here, so if we count the diagonals, that'd be 1 diagonal, 2 diagonals and a half, so we go a half, 1 and 2. And as you can see, we've got our rectangle shape. Now we just need to get a ruler and pencil and draw a nice rectangle. And that's it. So we reflected shape B, or rectangle B, in the line y equals negative x. And it's just very important whenever you're doing reflections to know what those lines y equals x and y equals negative x look like. Okay, let's have a look at our next topic. And our next topic is enlargements. And that's videos 104 and 104A on Corbettmaths. So in NM7, whenever we're doing enlargements, the enlargements may include fractional scale factors. So here's a typical question. It says enlarge by scale factor a half using -5 as the centre of enlargement. So we've got a fractional scale factor. Okay, so let's have a go at this question. So it says enlarge by scale factor half using -5 as the centre of enlargement. So let's find -5. So that's our centre of enlargement there. And we've got our original shape, our object, and we're going to enlarge it by a scale factor of half. That means that all the points in the image will be half the distance away from the centre of enlargement. So if, for instance, we looked at this point at the top of the kite, this point at the top of the kite is 1, 2, 3, 4, 5, 6 squares to the right, and 1, 2, 3, 4, 5, 6, 7, 8 squares upwards. So because we're using scale factor of a half, we're going to half those distances. So instead of going 6 to the right, we're going to go 3 to the right, 1, 2, 3. And instead of going 8 up, we're going to go 4 up. So 1, 2, 3, 4. So the top of our kite will move to here. Okay, now let's look at the left-hand side of the kite here. So this point is 1, 2, 3, 4 squares to the right, and 1, 2, 3, 4, 5, 6 squares upwards. So we're going to half those distances. So instead of going 4 squares to the right, we're going to go 2 squares to the right, 1, 2. And instead of going 6 up, we're going to go 3 up, 1, 2, 3. So that means that the left-hand side of the kite will move to here. The right-hand side of the kite, so we can kind of guess it's going to move to this point here, but let's check it. So going back to our centre of enlargement, it is 1, 2, 3, 4, 5, 6, 7, 8 squares to the right, and 1, 2, 3, 4, 5, 6 squares upwards. We're going to half those, so that'll be 4 to the right and 3 up. So 1, 2, 3, 4, and 1, 2, 3. So that's the right hand side of the kite. And let's be careful with the bottom of the kite because we need to make sure we get the right height here. So it is, whenever we look at our bottom of our kite, going back to the centre of enlargement, it's 1, 2, 3, 4, 5, 6 squares to the right and 1 up. So we're going to half our distances. So instead of going 6 to the right, we're going to go 3 to the right, 1, 2, 3. And instead of going 1 square up, we're going to go half a square up. So it's going to be there. And then we'll get our ruler and our pencil and we'll join those up. And that's it. So we've enlarged this shape by a scale factor of a half, so it's got smaller, using the centre of enlargement -5. If our scale factor of enlargement was a different number, perhaps a third, we would have divided all the distances by 3. If it was a quarter, we would have divided them all by 4. If it was 3/4, we would have divided by 4 and times by 3. Even if it was a top-heavy fraction, so for instance, if it was 3/2, you'd divide them all by 2, all the distances, and then multiply them all by 3, and then it would tell you where all the points would move to, and that's it. Okay, let's have a look at our next topic. So our next topic is combined transformations. So that will be whenever we do 2 or more transformations. So rather than just doing one transformation, so one reflection, translation, rotation, or enlargement, we may need to do one of them and then do something else. So let's have a look at our question. So we've got triangle H, so this triangle, is rotated 180 degrees about the point -2, -1. And then the image is then reflected in the line x equals -2. Draw the final image and label it A, and describe the single transformation that takes H to A. Okay, so let's start off by looking at our triangle, and we're going to rotate it 180 degrees about -2, -1. So -2, -1 is here. And we're going to rotate this triangle 180 degrees about that point, using that as the centre of rotation. So put the tracing paper over the top, mark on the centre of rotation, put the pencil on the centre of rotation, and rotate it 180 degrees. And then we move to here after you do that rotation. Okay, next we've been asked to reflect this shape, the image, in the line x equals -2. So remember the line x equals -2, that's a vertical line that passes through -2 on the x-axis. So we go to the x-axis, -2, so that's there. And the mirror line will be x equals -2, which would be this line, it's the mirror line. And what's actually great is, if we look at our mirror line, 2 of our corners of the triangle are already on that. So those 2 corners will be invariant, they won't move, they'll just stay where they are, there and there. And finally, our third corner of the triangle is here. So it is 1, 2, 3 to the mirror line, so we need to go 1, 2, 3. So we'll never reflect this triangle in the mirror line and move over here, and it would look something like this. And our second part says, describe the single transformation that maps H to A. If we look at H and A, you can see it's actually a reflection. There's been a reflection that takes H to A. And let's find out where the mirror line would be. So if we look at this point here, this bottom corner of A, and we count to the top corner of H, that would be 1, 2, 3, 4 squares down. So that means that our mirror line will be in the middle. So our mirror line will be going across here. So this will be our mirror line, the line y equals -1, because it's a horizontal line that passes through -1 on the y-axis. So that's the line y equals -1. And as you can see, it's a reflection. If we were to reflect h in that line, so going 1, 2 up, and then going another 2 up, 1, 2, at that point we move there. This point, moving 1, 2, 3, 4 up, and moving up another 4, 1, 2, 3, 4. And you can see it's a reflection. So there's been a reflection in the line y equals -1. And that's our mirror line, and that's it. Okay, so let's have a look at our next topic. So our next topic is similar shapes, and that's videos 292 and 293 in Corbettmaths. So similar shapes are shapes that are enlargements of each other. So if two shapes are mathematically similar, one is an enlargement of the other, which means all the sides are so many times bigger, maybe twice as big or 3 times as big, but all the angles are the same size. Now, one of the things that we looked at, I think it was in M6, whenever we looked at enlargements, what we found was that if we enlarge this shape by a scale factor 3, the area actually became 9 times bigger. And here are the rules, and this is part of the Corbettmaths revision card, that if the scale factor of enlargement for the sides is n, the scale factor for the area is n squared, and the scale factor for the volume is n cubed. In other words, if you re-enlarge a shape and the sides are perhaps 3 times bigger, the area will be 9 times bigger because 3 squared is 9, and the volume, if for instance it was a cube and we enlarge it by a scale factor of 3, the volume wouldn't actually be 3 times bigger. You would do 3 cubed, which is 27, so it would be 27 times bigger. If we enlarge the shape by a scale factor of 5, the area would become, well, 5 times 5 is 25 times bigger, and the volume would be 5 cubed, which is 125 times bigger. And that's really useful whenever we're dealing with similar shapes. So here we've got two similar shapes, two trapezia. If we have a look at this first trapezium, you can see one of the lengths of the parallel lines is 5 centimeters. And for the larger trapezium, the corresponding length has a side length of 15 centimeters, which if we look at it is 3 times bigger, because 5 times 3 is 15. That means, because the sides are 3 times larger, we will square that, and that's 9. So I mean the area is actually 9 times bigger. And if we were given the area of the smaller trapezium, which is 20 centimeters squared, and we wanted to find the area of the larger trapezium, we could do 20 times 9, which is 180. And that's it. If we were given the area of the larger trapezium, we would divide by 9, and then that would give us the area of the smaller trapezium. But if we know the scale factor of enlargement for the sides, we can square that to get the scale factor of enlargement for the areas, and we can cube it to find the scale factor for the volumes. And that's it. So this time we've got two cuboids, and we've got a smaller cuboid, which has a side length of 7 centimeters, so the length of it is 7 centimeters, and the length of the larger cuboid is 14 centimeters. And as you can see, the sides are 2 times larger, so that means the scale factor of enlargement for the sides is 2. That means if we want to find the scale factor for the volume, we will cube that. 2 cubed is 8. That means the volumes are 8 times bigger. So the volume of this cuboid will be 8 times larger than the volume of that cuboid. So if we do 100 times 8, that will give us the volume of the larger cuboid. 100 multiplied by 8 would be 800 centimeters cubed, and that's it. Okay, so the next topic is looking at giving our answers in terms of pi. Now, I've previously looked at topics such as circumference and area of a circle, volume of a cylinder, and so on. And in all of those questions so far, we've been given our answers as decimals. Now, I've actually hinted in previous videos that we could actually give our answer in terms of pi, and that's working exactly. So rather than giving a decimal, we're given an exact answer in terms of pi. So let's have a look at a typical question. So we've got a cylinder has got a diameter of 8 centimeters. So we've got a cylinder. So if by magic, we've got a cylinder and it's got a diameter of 8 centimeters. So that means that the width of it is 8 centimeters. So the whole way across the circle at the top or the bottom is 8 centimeters. And the height of the cylinder is 15 centimeters. So the height is 15 centimeters. So we've now got our sketch. Now what we need to do is work out the volume of the cylinder in terms of pi. And what that means is rather than giving our answer as a decimal number, we're going to give it as perhaps something like 100 pi or 75 pi. And that means we've got an exact answer. So rather than actually having to work it out and then rounding it, we can actually just give it in terms of pi. So the volume of a cylinder. So a cylinder is a prism. So we would find the area of the cross section. So in this case, a circle, and then multiply by how tall the shape is. So let's get the area of the circle. So the circle has got a diameter of 8. So the radius of the circle is 4 centimeters, and the area of a circle is pi r squared, so pi times 4 squared. Now 4 squared is 16, so that means that we would have pi times 16. And then if we just put them together, like in algebra where we'd maybe write 16y or 16x, we're just going to write that's equal to 16 pi. We're just going to put the number in front of pi. So that means the area of this circle is 16 pi centimeters squared. So that's the area of this circle. And rather than rounding that as a decimal number and then multiplying it by 15 and so on, what we're just going to do is use that 16 pi. So to find the volume of a cylinder, we've found the area of the circle. Now we need to times it by how tall or how long the shape is. So the height of the cylinder is 15 centimeters. So to get the volume, we're going to do 16 pi, the area of the circle, times by how tall the shape is, which is 15. So what we're going to do is we're going to do 16 times 15 and then get our answer and just put pi after it. So 16 times 15 is equal to 240 and then pi. So the answer would be 240 pi centimeters cubed. And that's it. So we've left our answer in terms of pi, and our answer would be 240 pi centimeters cubed. So we're not actually having to work out what 240 times pi is and then write that as a decimal number. We can actually just give it in terms of pi, and this is particularly useful on non-calculator papers. Okay, let's have a look at our next topic, and this is still working exactly. So we're going to do a Pythagoras question, and we're going to leave our answer as a surd, and then what that means is it's going to be a square root. So it's going to be a square root of something, but we're not actually going to work it out. So let's have a look at our question. So our question says, work out the length of x. Leave your answer as a surd, and a surd means something with a square root in it. So we've got a right angle triangle, and it's got two shorter sides of 5 centimeters and 8 centimeters, and we've been asked to find the length of x, the length of the hypotenuse of this triangle. So let's label our sides. So Pythagoras' theorem is a squared plus b squared equals c squared, where a and b are the two shorter sides, so let's label them a and b. And c is the length of the hypotenuse, which is the side opposite the right angle, so this would be our c. So let's substitute in our values. So instead of a squared, we're going to have 5 squared. And instead of b squared, we're going to have 8 squared. And that's equal to, and instead of c squared, we're going to have x squared. So let's work out our values. So 5 squared is 25, and 8 squared is 64. And that's equal to x squared. Now 25 plus 64 is 89, so we've got 89 equals x squared. And let's just turn that around, so we've got x squared equals 89. So normally at this point, what we do is work out the square root of 89, and then just round that to maybe 1 or 2 decimal places, and that's our answer. But this could potentially be on a non-calculator paper, or it could be that we don't actually want to round our answer, we want an exact answer. So what we're going to do is we're going to square root both sides here, so we're going to get x equals, and we're just going to write the square root of 89. And that's our answer. So we've left it as a surd, something with a square root in it. So x would be the square root of 89 centimeters. And that's it. Okay, let's have a look at our next topic. So our next topic is the product rule for counting, and that's video 383 in Corbettmaths. So the product rule for counting is a really useful technique to work out how many possible ways there are of doing things. So for instance, if there's n ways of doing a first task, and n ways of doing a second task, if we multiply those two together, we find out the total possible numbers of ways of doing those two tasks. So if for instance we went into a restaurant and there was 8 different starters and there was 10 different main courses, and we wanted to find out how many possible ways there are of choosing a starter and a main course, so one starter and one main course, and we wanted to list down all the possible options. If we do 8 times 10, and that gives us 80, that would tell us the answer to how many possible ways we can pick a starter and a main course. There would be 80 possible ways we can choose one starter and one main course. For instance, we could have the first starter with each of the 10 possible main courses. We could have the second starter with the 10 different main courses, the third starter with the 10 possible main courses, and so on up until the 8th starter and the 10 possible main courses. And that would mean there would be 80 possible combinations of a starter and a main course. So this product rule for counting is a really useful technique to work out how many possible ways you can do things. So let's have a look at an example, and this is the Corbettmaths revision card, and we've got Grace picks a 4-digit number. So she's got a padlock and she's going to choose a 4-digit code for it. The first digit is a prime number. The third digit is greater than 7, and we've been asked how many possible different 4-digit numbers can she choose. So let's look at each of the digits. So the first digit is a prime number, so that could be 2, 3, 5, 7, but it can't be 11 because that's got 2 digits. So she's got 4 possible options for the first digit. She can choose a 2, a 3, a 5, or a 7. So that means she's got 4 possible options for the first digit. The third digit is greater than 7, so that could be an 8 or a 9. We can't have 10 because that's got 2 digits. So the possible digits are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And 8 and 9 are the only two that are greater than 7. And because it's greater than, we're not going to include 7 itself. So there's 2 possible digits we can choose for the third digit. In terms of the second digit and the fourth digit, we've not been given any rules for those. That means they can be any of the 10 digits. It could be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 10 different choices for digit 2, and there's 10 different choices for digit 4. So what that means is, if we want to find out how many possible 4-digit codes you can choose, we could multiply these numbers together. We could do 4 times 10 times 2 times 10. And 4 times 10 is 40, times 2 is 80, times 10 is 800. So that means there's 800 different possible numbers you could choose. We could try and list them all if you wanted to, but with there being 800, I'd rather use this technique. So this is video 383 in Corbettmaths. If you want to try some practice questions on it, there's practice questions beside those as well. And also remember, in the description below, there's a link to that bumper booklet that accompanies this video. And so if you want to do a practice question on this, you can click that link and try that practice question. Okay, let's have a look at our next topic. So our next topic is called tree diagrams, and it's a probability topic, and a tree diagram is a really useful way of showing what can happen whenever 2 or more events take place. And it's video 252 in Corbettmaths. This is a very important topic, so I highly recommend you watch that video and try the practice questions as well. So let's have a look at our questions. Our question says, John and Dan are taking it in turns to throw a ball at a target. So we've got 2 different events. John's going to throw the ball at the target, and then Dan's going to throw the ball at the target. And what's great is this diagram will show us all the possible outcomes of what can happen. And we've been given some probabilities. So we've been given the probability that John hits the target is 0.6, and the probability that Dan hits the target is 0.7. Now before we get started, let's actually label the probabilities on the diagrams. Now the probability that John hits the target is 0.6. So let's work out the probability that John misses the target. Now it's certain that he does one of these 2 things. He's either going to hit it or he misses it. That means these 2 probabilities need to add together to be equal to 1. So if we want to work out this missing number, we're going to do 1 take away 0.6, and that would be 0.4. So these 2 probabilities we need to add together to give us 1. Okay, now we've got Dan throwing the ball at the target. Well, he could hit the target, which is 0.7. So the probability that Dan misses the target is 0.3. And below for Dan, again, we've got 0.7 is the probability that he hits the target, or 0.3 is the probability that he misses the target. Okay, so we've now got our tree diagram with our probabilities labelled on it. Now let's consider the outcomes of John throwing the ball and then Dan throwing the ball. Well, if we go along the branches, we can find out all the possible outcomes, and that's the great thing about a tree diagram. So let's start here, and John throws the ball and he can hit it, and then Dan can hit it. So we've got a hit and a hit, hit and a hit. So that's a hit and then a hit. Then we could have John hits the target and Dan misses the target, so that would be a hit and a miss. So that's a hit and a miss. Now if we go down this way, John can actually miss the target, and then Dan can hit the target, so that'll be a miss and a hit. And finally, John can miss the target and Dan can miss the target, so that'll be a miss and a miss. So we've got all the possible outcomes here. We've got a hit hit, hit miss, miss hit, and a miss miss. And what's fantastic is we can use the probabilities we've been given in the question to work out the probabilities of a hit hit, hit miss, miss hit, and miss miss really easily. And all we do is multiply the numbers along the branches. So if we wanted to work out the probability of John hitting the target and Dan hitting the target, because it's and, what we do is we multiply the probabilities together. So we're going to do 0.6 multiplied by 0.7. So we go along the branches and we do 0.6 multiplied by 0.7. So let's write that down. 0.6 multiplied by 0.7 is equal to 0.42. So the probability of John hitting the target and Dan hitting the target, hit, would be 0.42. Next, let's work out the probability of John hitting and Dan missing, so a hit miss. So that'll be 0.6 multiplied by 0.3. So 0.6 multiplied by 0.3 would be 0.18. Next, we could have John missing and Dan hitting, so that would be 0.4 multiplied by 0.7. So 0.4 multiplied by 0.7, and that'll be equal to 0.28. And finally, we've got a miss, so that's John missing and Dan missing. So that would be 0.4 multiplied by 0.3. So 0.4 multiplied by 0.3 would be equal to 0.12. And what's great is if we add these probabilities together, 0.42, 0.18, that's 0.6, plus 0.28, that's 0.88, and then plus 0.12, that gives us 1. Because obviously one of these 4 things will have to happen, either hit hit, hit miss, miss hit, or miss miss. Okay, so let's go to our question. So our question says, what is the probability that at least one man hits the target? So at least one man hits the target means either one of them could hit it or both of them could hit it. So hit hit, that would work. Hit miss, yep, one of them's hitting the target, that would work. Miss hit, yep, one of them's hitting it, that would work. But miss miss wouldn't work. So that means we're interested in this probability, and this probability. And we want to find the probability that either it's a hit hit, or a hit miss, or a miss hit. So if we add these 3 probabilities together, we will find the probability that at least one man hits the target. So we could do 0.42 plus 0.18 plus 0.28. And when we do that, we get 0.88. So the probability that at least one man hits the target would be 0.88. And that's it. Okay, let's have a look at our next topic. So our next topic is independent events. And independent events is a bit like tree diagrams, but we're just not going to be using our tree diagram. So then this would be 249. So we've got Naomi has a biased spinner. So here we've got a spinner and it's biased, so it means that it's not equally likely to land in any of the sections. So we've got the probability that the spinner lands on red being 0.1. The probability that it lands on white is 0.4. The probability that it lands on black is 0.3. And the probability that it lands on brown is 0.2. And she spins the spinner twice. And the question says, what's the probability that the spinner lands on black twice? Now you could draw a tree diagram here and you could do 1, 2, 3, 4 branches for the first outcome, the first spin. And then we could do another 4 branches for each one of them, like so. And it'd be quite complicated. What would be great is if we could do this question without drawing out the tree diagram. So we want to find the probability of a black and a black. Now the probability that the spinner lands on black anytime is 0.3. So what we're going to do is, if we imagine our branches, we're going to do black and black. So that would be 0.3 multiplied by 0.3, because that's the probability for black multiplied by the probability for black. So 0.3 multiplied by 0.3 would be 0.09, and that's it. If we wanted to find out the probability it landed on brown twice, we would do 0.2 times 0.2. If we wanted to find out the probability it lands on white twice, we would do 0.4 times 0.4, red twice, 0.1 times 0.1, and so on. Okay, and that's it. So let's have a look at our next topic. Okay, let's have a look at our next topic. So our next topic is negative indices, and it's a number topic because it's in red, and it's video 175 on Corbettmaths. Now we talked about negative indices briefly earlier on whenever we looked at the algebra topics and laws of indices. Now let's look at it in a bit more detail. Now let's consider this pattern where we've got 5 to the power of 3, 5 to the power of 2, 5 to the power of 1, 5 to the power of 0, 5 to the power of negative 1, and 5 to the power of negative 2. So 5 cubed, well 5 times 5 times 5 is 125. 5 squared, well that's 25, 5 times 5 is 25. 5 to the power of 1, well that's just a 5, so the answer would be 5. Okay, next we've got 5 to the power of 0. Well, 5 to the power of 0 is 1. Okay, and next one is 5 to the power of negative 1. Well, if we look at our numbers here, we've got 125, 25, 5, and 1. Now there's a pattern here. To go down in this pattern, we're dividing by 5. We're dividing by 5. We're dividing by 5. We're dividing by 5. And then if we want to find out our next one, we would just divide by 5 again. So if we do 1 divided by 5, well that'd be 0.2, or we could just write it as a fraction, which is 1 over 5. If we want to get our next answer, we could divide by 5 again. Okay, so we do 1 over 5, or 5th divided by 5, so that'd be 1 over 25. Now what's actually quite useful to spot here is, because we've got 5 to the negative 2, that's the same as putting 1 over and 5 squared. And 5 squared is 25. So that's our rule. If we have x to the power of negative n, that's the same as 1 over x to the n. So you can just put 1 over and then just use the positive power. So here, if we were asked to work out 2 to the power of negative 3, we could just put 1 over and then just write 2 cubed, changing our negative 3 to just 3. And then 2 cubed is 8, so the answer would be just 1 over 8, or 1/8. So 2 to the power of negative 3 is 1 over 8. Next, 10 to the power of negative 2, well we would put 1 over and then just write 10 squared. And 10 squared is 100, so the answer would be 1 over 100. So if we had 10 to the power of negative 2, our answer would be 1 over 100. And that's it. So if we want to work out a negative power, you just put 1 over and then just use the positive power on the denominator. Okay, let's have a look at our next topic. So our next topic is called standard form, and that's videos 300 to 303 in Corbettmaths. Now standard form is a really useful way of writing very large or very small numbers very quickly and easily. So rather than writing a large number out lots of times, we can use standard form to help us. And a number is in standard form if it's in this format, where we've got a number between 1 and 10, so it's a number bigger than or equal to 1 but less than 10, so for instance 1 or 4.22 or 9.9, multiplied by 10 to a certain power, so maybe 10 cubed or 10 to the power of 8 or even 10 to the power of negative 3. And we're going to look at how to write some large numbers in standard form and some small numbers in standard form. And I'm actually going to do this part of the video twice. I'm going to actually use two different techniques here, because some teachers will use a technique where they add zeros or move decimal points, and some teachers will move the digits and say the decimal points have to stay fixed. My job is to help you and make sure that I cover the way that you are familiar with, and I don't want to confuse you by using just one technique and then you think, well, hold on, my teacher talks about it in a slightly different way. So to begin with, I'm going to talk about adding zeros and moving decimal places, and then I'm going to do the questions again by moving the digits rather than the decimal points. So first of all, we had 7,000 and we wanted to write it in standard form. Well, a number between 1 and 10 to choose. Well, I'm thinking 7 would be a good choice, and then we're going to multiply it by 10 to a certain power. Now whenever we have a whole number and we multiply by 10, we add a 0 on. So 7 times 10 is 70 by adding a 0 on. If here we want to add 3 zeros on, so what we actually want to do is multiply 7 by 1,000, and that would be 10 cubed, because 10 times 10 times 10 is 1,000. Now notice that if you have a whole number and you want to add 1, 2, 3 zeros on, the power would just be 3. So the answer would be 7 multiplied by 10 cubed. If we had a number such as 80,000, which is 8 followed by 4 zeros, we could have 8 multiplied by it, and because this is a whole number, we could say it's 10 to the power of 4, because it's 1, 2, 3, 4 zeros. Okay, let's have a look at our next one. So our next one is to write 2,500,000 in standard form. So we're going to choose a number between 1 and 10. Now we've got 2, 5, so we're going to choose 2.5 here, because that's a sensible number to choose between 1 and 10. Now what we're going to do is we're going to figure out if we have 2.5, how many times we need to move the decimal point to get it at the end of the number. So we want to move the decimal point from here to here. So we would move it 1, 2, 3, 4, 5, 6 times. So that means we need to multiply 2.5 by 10 to the power of 6, because that would move the decimal place 1, 2, 3, 4, 5, 6 places to the right. Okay, next let's look at some small numbers. So here we've got 0.0000004. So that would be 4 would be our number we would choose between 1 and 10. We need to multiply by 10 to the power of. Now we've got a small number here which is less than 1, so this is going to have a negative power, and we need to figure out how many times we move the decimal point to get from 4 to be this number. So if we had 4, the decimal point would be here, and we would move it 1, 2, 3, 4, 5, 6, 7 times. So the answer would be 4 times 10 to the power of negative 7. Or a student once actually told me a bit of a shortcut. They said, well, so there's 1, 2, 3, 4, 5, 6, 7 zeros in front, so you can just write 4 times 10 to the negative 7. And I thought that was quite a neat way to do it, is just count the number of zeros. Okay, and finally, we've got 0.018, and if we want to write that in standard form, well, it's going to be 1.8, because that's the number we would choose between 1 and 10, multiplied by 10. And now we've got 1.8, so the decimal point's here, and we want to move the decimal point 1 twice to the left, so the power would be negative 2. Alternatively, you might have spotted the pattern that my student mentioned to me, and because it's a small number, a 0-point number, and it's got 2 zeros, it'll be to the power of negative 2. Okay, now let's have a look at these questions using the other approach, so let's get rid of that. Okay, let's have a look at our first question. So our first question is to write 7,000 in standard form. So we want a number between 1 and 10. And a sensible number to choose here would be 7. And we're then going to have multiplied by 10 and to a certain power. Now if we have 7, 7's in the units of the ones column, and we want to move it 1, 2, 3 columns to the left. So we want to move this 7 3 columns to the left. So we would multiply by 10, 100 and 1,000. So actually 1,000 is 10 cubed. So if we want to move it 3 columns to the left, we have a power of 3. So the answer would be 7 multiplied by 10 cubed. Next, we've got 2,500,000. So we've got to choose a number between 1 and 10. So a sensible choice here would be 2.5 and then times 10 and to a certain power. So let's put 2.5 in. So the 2 would be in the ones column or the units column there. We'd have our decimal point and we'd have our 5. And we want to move the digits 1, 2, 3, 4, 5, 6 columns to the left. So we would have to the power of 6. So 2.5 times 10 to the power of 6 would be 2,500,000. Okay, let's have a look at some small numbers. So we've got 0.0000004. So that would be, well, we need a number between 1 and 10. So we're going to have 4 times 10. Now, because this is a small number, we're going to have a negative power, because 10 to the negative 1 is 0.1. So we'll be multiplied by 0.1. 10 to the power of negative 2 would be 0.01 and so on. So we want a negative power, a very small number. And if we put our 4 in our units or our ones column there, we want to move the 4 1, 2, 3, 4, 5, 6, 7 columns to the right. So because we want to move it 7 columns to the right, the power would be negative 7. So the answer would be 4 multiplied by 10 to the power of negative 7. And finally, 0.018, well, a sensible number to choose between 1 and 10 would be 1.8. And we want to multiply it by 10 to the power of negative something because we want it to be smaller. And we've put our 1.8 in our columns. Our 1 is in our units column or our ones column, and we want to move it to our hundredths column. So we want to move the 1, 2 columns to the right. So we want to times it by 1.8 times 10 to the power of negative 2. Okay, next. Now let's look at how we would write numbers that are almost in standard form in standard form. So if we have a look at this number, 562.8 times 10 to the power of 5, this number is almost in standard form. And what I mean by that is we need a number between 1 and 10, and this number at the front isn't between 1 and 10. So we need to make it between 1 and 10. So if I had the number 562.8, I would divide that by 100, because if I divide that by 100, I would get 5.628, and that's between 1 and 10. But if I divide one number by 100, so for instance, if I had 700 multiplied by 2, the answer is equal to 1,400. If I divide this number by 100 and get 7, I would need to multiply this number by 100 to get 200 to still keep the same answer. So if I've divided this by 100, I need to multiply this by 100 to make sure our answer stays the same. So it's going to be 5.628 multiplied by 10. So if I multiply this by 100, I'd multiply by 10, so that'll be 10 to the power of 6, and I multiply by 10 again, so that'll be 10 to the power of 7. So the answer would be 5.628 times 10 to the power of 7, and that's it. Okay, let's have a look at another one. Okay, this time we've got 0.0024 times 10 to the power of 9. Now this isn't a standard form because this number needs to be between 1 and 10. So we're going to have to write 2.4 here, because that would then make sure that we would have a number between 1 and 10 at the front. And then we would do multiply by 10 to the power of something. So we multiply this by, well, we've moved the 2, 1, 2, 3 places to the left. So we've multiplied this by 1,000. So if we multiply this by 1,000, we need to divide this by 1,000. So dividing it by 10 would be 10 to the power of 8. Dividing it by 10 again would be 10 to the power of 7. And dividing it by 10 again would be 10 to the power of 6. Or another way to look at it is if we were dividing it by 1,000, remember that's 10 cubed. And then if we take away the powers, we get 10 to the power of 6. And that's it. So just make sure that if you have a number that's almost in standard form, if you make the number at the front 10 times larger, you need to make the times by 10 bit 10 times smaller to make sure that the answer stays the same. Okay, next. Okay, let's look at how to do our arithmetic with numbers in standard form. So how to do adding numbers in standard form, multiplying numbers in standard form, dividing numbers in standard form, and so on. Now, with adding numbers in standard form, there's no set rule. So if I had 5.3 times 10 to the power of 7 plus 7.96 times 10 to the power of 8, the way I would do this question would be to write them out in full. So I'm going to write our 5.3 times 10 to the power of 7 in full. So that would be 5, 3, and then 1, 2, 3, 4, 5, 6 zeros. And then we've got 7.96 times 10 to the power of 8 will be plus 796. So that'd be 796, and then we would then have another 6 zeros, 1, 2, 3, 4, 5, 6, and then we need to add these numbers together. And whenever we're adding them together, I'm just going to use the column method. So let's line them up. So we've got 7, 9, 6, and then 1, 2, 3, 4, 5, 6 zeros, 5, 3, and then 6 zeros. So 1, 2, 3, 4, 5, 6, and then 3, 5. Okay, and then we're going to add them. So let's just add them and see what we get. So it would be 0 plus 0 is 0, 0, 0, 0, 0, 0. We've then got 6 plus 3 is 9. 9 plus 5 is equal to 14. So put the 4 down, carry the 1. And 7 plus 1 is equal to 8. So the answer would be 849 million. Or we might want to write it in standard form again. So it would be 8.49 times 10 to the power of 1, 2, 3, 4, 5, 6, 7, 8. So it would be to the power of 8. And that's it. Okay, let's have a look at our next question. So the next question is multiplying numbers in standard form, and I like this because we can now put together our laws of indices. If we have 9 times 10 to the power of 4 multiplied by 2 times 10 to the power of 5, so what we can do is we can multiply the numbers at the front. We can do 9 times 2 is equal to 18, and then we can multiply the 10s to the powers. So we could do 10 to the power of 4 multiplied by 10 to the power of 5. And whenever we're multiplying things with the same base, they're both 10 to the power of something, we add the powers. So we would do 10 to the power of 4 plus 5 to the power of 9. So that's not our answer, because that's 18 times 10 to the power of 9. Remember, if for our answer to be in standard form, we want it to be between 1 and 10. So we're going to do 1.8 times 10. Now we've made 18 10 times smaller, so we need to make this 10 times larger. So 10 to the power of 9 times by 10 would be 10 to the power of 10. So the answer would be 1.8 times 10 to the power of 10. Now, as well as being able to do this in a non-calculator paper, it's also important to be able to do it in a calculator paper. So let's have a look and see how we would type this in our calculator. So on our calculator, we've got our standard form button here, down at the center there at the bottom. We've got our multiply by 10 to the power of x there. Now, whenever I'm doing a question like this, I tend to like to use brackets. So I would write it like this. So I would open up my brackets to begin with. I would press my 9, because that's the number between 1 and 10 we're going to use, and then I would press the standard form button there. And then you would get, it would come up with 9 times 10, and then you'd press 4, and that would be how you type in 9 times 10 to the power 4. It looks something like this, and then close brackets. So you open up your brackets, you press 9, the standard form button, and then press 4 to show that the power is 4, and then close brackets. Then press times, and then for this 2 times 10 to the power 5, you're going to do 2, the standard form button, and then 5, and then close brackets and press equals. And you should get this as your answer. It'd be a good idea to practice that now. Get your calculator and try typing this in. And the answer in your display should look something like this, where we had 1.8 times 10 to the power of 10, and that was our answer. And that's it. Okay, let's have a look at our next question. So this time we've got a division question, and we've got 4.5 multiplied by 10 to the power of 7 divided by, or over, 9 times 10 to the power of negative 5. So we've got a large number divided by a very small number. And whenever we divide by a very small number, it's going to get even bigger. So let's have a look at this question and see what we do. So we've got 4.5 times 10 to the power of 7. And we're dividing that by 9 times 10 to the power of negative 5. So we're going to do 4.5 divided by 9. Let's actually do that quickly. Now I know the answer is 0.5, but I'm just going to show you how. 4 divided by 9 is 0, remainder 4, and 45 divided by 9 it would be equal to 5. So that would be equal to 0.5. So 4.5 divided by 9 is 0.5. Then we've got our multiply by 10 part, so we've got 10 to the power of 7 divided by 10 to the power of negative 5. And remember, whenever we're dividing, we take away the power, so we've got 7 minus 5. And 7 minus 5 would add on the 5 would be multiplied by 10 to the power of 12, because 7 minus 5 would be 12. So we would get 0.5 multiplied by 10 to the power of 12. Now this isn't in standard form because this needs to be between 1 and 10. So we're going to multiply that by 10 to get 5, but we need to divide this by 10. So 10 to the power of 12, take away one of those 10s would be 10 to the power of 11. So that would be 5 multiplied by 10 to the power of 11. Okay, let's have a look at our next question. So this time we've got a situation that involves standard form. And the question says, an asteroid travels at 25 kilometers per second. And we're asked, how far does it travel in 1 hour? Give your answer in meters and in standard form. So we've got an asteroid that travels at 25 kilometers. Now, because we've been asked to give our answer in meters, let's change this 25 kilometers into meters. So that would be 25,000 meters, because there's 1,000 meters in a kilometer. So it's traveling at 25,000 meters per second. And we're asked to find out how far it travels in 1 hour. So let's work out how many seconds are in 1 hour. So there's 60 seconds in a minute, and then there's 60 minutes in an hour. So if we do 60 times 60, that's equal to 3,600. So there's 3,600 seconds in 1 hour. And we've been asked to work out how far does it travel. So remember, we've got speed, distance, and time. So distance is equal to speed times time. So if we multiply the speed by the time, because it travels 25 kilometers every second and it travels for 3,600 seconds, if we multiply those two together, we should get our answer. So we've got 25,000 multiplied by 3,600. And we get that's equal to 9 followed by 7 zeros, or 90 million, so 90 million meters. Now the question says to give our answer in standard form. So this is a very large number, so we want to give this in standard form. So a number between 1 and 10, well, let's choose 9, multiplied by 10 to the power of 1, 2, 3, 4, 5, 6, 7. So the answer would be 9 multiplied by 10 to the power of 7 meters. Okay, let's have a look at our next topic. So our next topic is direct proportion, and that's video 254 in Corbettmaths. And here's part of the Corbettmaths revision card, and we're told that C is directly proportional to the square of D. So let's write that statement down. So we've got C is directly proportional, so we'll use the proportion symbol. Some of my students call it fishy, but the proportion symbol to the square of D. So that means D squared, because it says the square of D. So if we read this, it says C is proportional to D squared. C is directly proportional to D squared. Sometimes the question might say it varies directly, and that means the same as directly proportional. And then we've got some information, and this information is going to be really useful. We're told when C is equal to 200, D is equal to 2. So let's write this out again, and let's get rid of this proportion symbol. So let's write down C and then equals, and then we'll put in a K, and that K is the constant of proportionality. So it's a certain value we're going to find, multiplied by D squared. So we've got C equals K times D squared. We've got rid of the proportion sign and we've put in the K, which stands for the constant of proportionality. Now what we're going to do is we're going to substitute in our values. We've got C is equal to 200. So we've got 200 equals K multiplied by, and we've got d squared. Now d is equal to 2, so it's going to be 2 squared. Now let's work this out. So we've got 2 squared is equal to 4, so we've got 200 equals k multiplied by 4. And if we divide both sides by 4, we get 50 is equal to k. So k is equal to 50. And let's put that back into our formula. So we've got c equals, instead of k times d squared, we're going to have c is equal to 50 times d squared, or 50 d squared. And that's our formula. And what I'm going to do is I'm going to put a box around it. It's very important, and that's what we would use for the rest of this question. So that's how you approach directly proportional questions. And I'm not finished yet, but that's how you approach them. So you write down the statement you're given with the proportion symbol. You then get rid of that proportion symbol and put in a k for the constant of proportionality, a certain number we've got to work out. In this case, it was 50. Then there'll be some information that you can put into your formula that has the k to work out what the value of k is. And then once you find it, then you've got your formula, which is really useful. Okay, so the next part of the question says, find c whenever d is equal to 5. So d is equal to 5. So c is equal to 50 multiplied by d squared. But d is equal to 5, so we're going to have c is equal to 50 multiplied by, and instead of d squared, it's going to be 5 squared. Now remember our order of operations, we have to do squaring before we do any multiplication. So we're going to do 5 squared is 25, so c is equal to 50 multiplied by 25. And then finally, 50 multiplied by 25 is 1,250, and that's it. And if you look at the Corbettmaths revision card, there'll be a step-by-step guide on how to do that, and these revision cards will be really useful for you. If you do have a set of the higher revision cards, it's really useful, and there's a link to it in the description below. And one other thing that's useful with direct proportion is to know what the graphs look like. And here are some situations on what their graphs look like. If you have y is directly proportional to x, that means as x increases, so does y, and the graph looks something like this. This is a nice straight line going up like that. Okay, next one is y is proportional to x squared, and the graph of that will look something like this. It's half of the quadratic graph, so it starts at the origin 0, 0 and curves upwards like that. And finally, if we had y is proportional to the square root of x, it'll look like the square root of x graph, so it would start at 0, 0 and then go upwards like that. And that's just some of the proportionality graphs which might be useful for you. Okay, and that's it. So in this video, we've spent about 5 or so minutes going through all of the M7 topics. If you need any extra help on any particular topic, the video numbers are there so that you've got the videos you can watch, which give you a slightly more detailed explanation as to each of the topics. I really hope this has been useful for you. So for M7, also make sure you're really confident with the M6 and M5 topics, and make sure you brush up on your M3, M2 and M1 topics as well. A link to this revision checklist is in the description below. Make sure you print it, stick it on your wall, save it on your phone, whatever. Make sure you know this checklist so you know all the topics you need to know and you know how to get help on each of them. Also remember, accompanying this video was the bumper book of questions, so the ultimate CCEA M7 revision question booklet. Again, you can click the link below. As you've been watching this video, you may have been writing notes, but it's also useful to do some practice as well, and this booklet has a question on every single topic we've gone through today. Also, I use quite a lot of the Corbettmaths revision cards as we went through the video. The higher revision cards will be very useful for you, and there's a link to them in the description below. Also for M7, I'd highly recommend you look at the higher and higher plus 5 a days. They are available in book format as well. And I really hope you found this video useful. We've gone through the M7 topics. I really hope this video has been useful. If it has, please like it, please subscribe to the Corbettmaths YouTube channel, and all the very best of luck with your studies.